The multiplexers, decoders, multipliers, adders, and all that sort of stuff finished us up with combinational logic. Combinational logic is logic that basically is the output is dependent on the state of the inputs. We're going to be moving next into sequential logic. Where the output is determined by not only the input, but the state of the circuit before. So you have your inputs, your logic, and the output feeding back into the input of the logic circuit. Now, as kind of a side topic, there is what is known as a clock that is going to be used. It's often abbreviated CLK. It is a series of pulses. They set the timing for the circuits. They have a rising edge and a falling edge. Where the clock signal goes up and the clock signal comes down. These, the time that it takes to rise and fall are the rising time and the falling time, and the fall time. It is not instantaneous. It can be measured. So it's not a true square wave. It is actually a slope where this is the rise time and this is the fall time. So things don't happen instantaneously. All right. These clock signals will be important when we get into sequential logic a little bit more in depth. One of the most simple sequential logic circuits is the SR latch. Which consists of two cross-coupled NOR gates Whoops, no, that's not right. Like so. Can also be used with NAND gates as well, but this is Q and Q prime. Q is separate, is on the next level, the opposite level as the S input. It is called the SR latch because the S is for set and the R is for reset. The state table for an SR latch is if S and R are both 0, these two are unchanged. It'll hold the state that it was in prior to the S and R both going low. If R is set and S is not, then Q is 0, Q prime is 1. If this is 0 and this is 1, the output for this is, with a 1 is going to be 0, regardless of what this is, and the 0 is going to come to here. 0 and 0 is going to be a 1, and Q prime will be 1, and Q will be 0. If R goes back to 0, the 1 here, the 1 on Q prime will feed back into here. 1 and 0 on the NOR gate is a 0, which keeps this a 0. This is 0, this is 0, keeps that as a 1. Okay? And the same logic applies to the S being set and the R being 0, except for its opposite. S will set the Q, and Q prime will go to 0. Now, what makes a SR latch difficult to deal with is with 1 and 1. That's not allowed. It's indeterminate. It basically they oscillate until one or the other of S and R goes to 0, and when that occurs, it will be either set or reset depending on which input goes to 0 first. So 1 and 1 on the SR latch is not allowed. It is an indeterminate result. Both will breed high and low, oscillating back and forth as fast as the circuit will allow. The other variety, the other way of doing the SR latch is with NAND gates. And it's primed so that with this, the Q is on the same level as the S, and the Q prime is on the same level as the R. But the states for this S, R, Q, and Q prime 0, 0 is not allowed. It is indeterminate. 1, 0. I'm sorry, 0, 1. 0, 1 on the set sets the Q and puts the Q prime to 0. And then the other direction resets the Q. R is the reset, active low, and the 1, 1 is the no change state. This is why I primed the S and R, because they are active low. A 0 on the set will set the output Q to 1. A low on the R prime will reset Q to 0. But again, you still have the not allowed state. In this case, 0, 0 is not allowed. It is the indeterminate state. Continuing with the SR latch, one way to keep things from being indeterminate is to add an enable pin to the input. And this is typically done with the NAND version. So you have the NAND. And all right. So your clock or enable pin will allow you to send in the inputs from the SNR and invert the output for your inverted input SR latch. So this is your SR latch, and this is S prime, and this is R prime. Now the state table for this, 0 doesn't matter on the SNR. There's no change. With the 1 here, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1. So there's no change here either with SNR being 0. And the R and the enable on will make R prime 0, and then follow this over here. It'll give a 1 on the 0 on the Q and 1 on the Q prime. Likewise, the same logic applies to the set. And again, there is the not allowed. So that is a let me. This is the clocked SR latch. As you can imagine, this is one of the most basic forms of memory. When you put a 1, for example, in Q, and then disable the clock, there's no change. It stores that bit in memory in these two cross-coupled NAND gates. So this is we're building up to basically create memory here, a form of RAM memory, random access memory. You still have the problem of the not allowed state. Anybody see a obvious way to eliminate that state, that possibility? Just add one more little thing. I'm sorry? Where? No, close. So put it over here. You're on the right track. You have your SR latch. Your clock enable. Your SNR and your clock. Make sure S and R are not both ones. So you place an inverter between the S and R. We'll call this an input D. That way, you still have the no change state when the enable is off. When the enable is on, you can't have this, and you can't have this. You just have data coming in and going out the queue. This is called a transparent D-type latch because it stores data on your outputs when the clock is low, when the enable is low. So when the enable is low, it latches whatever was on D at the time on the falling edge of the input clock or enable. I should put the enable here. So you can see that enable and you 0 doesn't matter, no change. 1 1 0 1 Q 0 Q prime is 1 Q is 1 Q prime is 0. So that eliminates the not allowed state that is possible with the previously discussed circuits. The D-type latch is also called a transparent, The transparent D-type latch is also called just a regular transparent latch, depending on the literature you're looking at. Now, to make these easier, so you don't have to draw out a bunch of NAND gates and inverters and all that sort of stuff, we have the graphical symbols for the latches. SR is that's with the NOR implementation. The NAND implementation is S prime, R prime, with the inverted inputs and one inverted output. That's SR, S prime, R prime. And the D-type latch is D enable. So you have those three different symbols that are used for basic memory locations. I haven't confirmed this, but I think these form the basis of what's called static random access memory. They will hold basically they will hold a piece of data in memory as long as there is a charge on the chips that they're on. I'm not sure about that though. As opposed to dynamic random access memory that has to be refreshed every so often, but takes up less space on a chip. So this takes up more space on the chip, but it's fairly fast. And as long as there's power on the chip, you have the memory. You have the data in memory. I think I'm going to go ahead and stop there, but questions? This is the NOR, and this is the NAND. Implementation, but they function similarly. Just one has inverted inputs. And the other has regular active high inputs. Any other questions? I know feedback and keeping track of what's going on with sequential circuits is a little bit more challenging than regular sequential, rather than regular combinational logic. But you just look at the breakdown of what is what. This is a latch, and this is just regular combinational logic here. So, all right. Well, have a good day. See you on Wednesday, and we'll discuss flip-flops.